Prime Target is a limited series on Apple TV. The premise is that a genius has found a way to find patterns in prime numbers. It's a fantasy, and some have quibbled with the history of math as it's presented in the show. I agree, it's important to be accurate. However, the show's a big-budget affair, and it's very well produced. Prime Target is set entirely in Europe. Leo Woodhall plays Edward Brooks, the main character, a student at Cambridge University in England. The show also gives favorable nod to Gen X star Martha Plimpton as a NSA handler to Quintessa Swindell, who plays a very smart but compromised NSA agent assigned to follow notable cryptographers who might one day have a breakthrough in their careers. Well, Brooks has such a breakthrough, and not only does Plimpton's NSA character want him, others do as well. Sometimes you just have to sit back and appreciate a well-produced show on the surface and go with it. Hopefully, what the show does is expose the average viewer to just how precarious our economic world is to cryptographic standards based on a 3-decade-old RSA algorithm. Several times they talk about how Brooks' discovery could render all currently used encryption broken. Why? RSA uses 2 large prime numbers to produce a modulus, which is used to secure your Amazon transactions, your banking, even your health information. Today, it would take that Dell laptop hundreds, if not thousands of years to decrypt one RSA encrypted transaction. So for the moment, your data is safe, but there is a real-world threat coming. Quantum computing. NIST has already started soliciting for post-quantum encryption standards, and they recently arrived at 4 post-quantum standards that we should use. And in November 2024, the U.S. government mandated that systems be upgraded to handle these and others by the year 2029. And I said, and others. Maybe you see where this is going. Instead of building our entire encryption system around one algorithm, like RSA, we need to become crypto-agile. That is, we need to have the ability to swap out algorithms as needed. Trouble is, most organizations today don't even know what encryption they're using, or where. Worse, there are perhaps millions of OT systems out in the field with embedded encryption, some of which are already depreciated. This is a story about cryptographic debt that extends to operational technology, where critical infrastructure like energy, water systems rely on old, often unencrypted devices that are hard to replace. I'm Robert Vamosi. This is Error Code.
I'm Dave Krauthamer. I'm a field CTO at QuSecure. QuSecure came about a couple of years ago. So we've seen in cybersecurity, we've had kind of static, there's been a really static nature to cryptography and how we secure devices. And we haven't really had a need to upgrade the cryptography on devices because it's a really hard math problem. But with the onset of AI and just brute force computing and then quantum computers, these algorithms and keys are now under threat. And there's 20 plus billion devices out there that now are under some threat. So QSecure was born out of the realization that there's going to be a significant crypto modernization to manage crypto and crypto agility. So QSecure focuses on that modernization process of really creating secure comms and then the ability to kind of swap out cryptography with the latest, greatest, whether that's here today or here tomorrow, whether it needs to be swapped out in a minute or 5 years. We give you then network visibility across and the ability to swap it all out in real time.
I've spoken with QSecure before. Back in episode 4 of Error Code, I spoke about hacking the quantum realm with Skip Sanzeri, the CEO of QSecure. Then, about a year later, in episode 24, I spoke with Skip again, this time about securing satellite communications with quantum cryptography. It's not necessary to go back and listen to those earlier episodes before continuing. What Dave and I are going to talk about in this episode is something different. The cryptographic research being done to create post-quantum encryption systems that are agile in order to change as things go forward. People may have heard of quantum computing, but what about quantum cryptography? How do you explain that to the layperson? Should they ask?
Yeah, let's go back to conventional computing. So, conventional computing that we all use and rely on uses a word size that's pretty small. So it's like 64 bits. We've all heard of a 64-bit. So that means that they can process a little bit of information at once. And so computers today are really good at linear problems that go from A to B to C, which is a subset of all problems in the universe. If you said what problems are linear, balancing your checkbook's linear, there are linear processes, but there's problems in science, in nature, that are not linear, that just have an infinite number of points. The conventional computers, like I said, are really good at doing linear things. But when you run into this problem set that's nonlinear, like cracking these certain types of math, you need a new kind of compute. Take that 64-bit word and compare it to a quantum processor where we have qubits, which are ones, zeros, or anything. And the word size gets exponentially bigger. So a 64 qubit processor is 2 to the 64th in word size, which is like all the data stored in the world in the last year in one instruction. So you can solve these massively complex problems like navigating through a maze in every direction at once. So it just opens problem solving up to just an infinitely broader capability.
So I'm wondering how Dave explains to his family and friends what quantum cryptography is.
Yeah, great question. So let's demystify the whole thing. Quantum cryptography is just better math. So right now, the math we use to secure our devices is based on prime number factoring, and which is actually a really hard problem for computers to solve. So factoring prime numbers, just computers really struggle with it. It takes tens of thousands, if not millions of years to factor prime numbers. So all our devices use, you might have heard of RSA, and RSA is prime number factored math. And so the way devices scramble and unscramble data is they have an algorithm and a key, and that algorithm and the key then scrambles it and descrambles it via prime numbers. So post-quantum or quantum cryptography is just better math. So if the current math, the prime number factored math, is under attack, then there's new math. They're called lattice-based math. It's not actually new math that is immune to quantum attacks. And so it's just better math. There's nothing really quantum about post-quantum cryptography or post-quantum math. It's just better math and more defensible against a quantum computer.
So earlier, Dave mentioned that cryptography has been stable. Already we've seen AES and we've seen other algorithms fall because they've become cracked, meaning someone can figure out how to decipher them. And this is kind of a slow process, although it's sped up a bit. And what we're talking about is literally a revolution in the sense that quantum computing can crunch these numbers much, much faster.
Yeah, like if you look at the history of cryptography and you go back to the Caesar cipher, which was Julius Caesar's cipher, where they like threw everything off one character. And, cryptography has been around for a long, 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 long time. And in the computer age, it's gotten better and better math. But it's always, since time immemorial, been a way to thwart people from reading your stuff. And, starting in the 60s or 70s, IBM came out with DES, and it's progressed slowly. And it's largely been embedded in a device. So we've never really paid much attention to it. It's been in a program or a device or a piece of hardware because it took 10 or 15 years to deprecate one of these algorithms or ciphers. And then so we had plenty of time to prepare for the next upgrade cycle. And now we're just all of a sudden, first off, a couple of years ago, when we started QuSecure, people were like, well, there's never going to be a quantum computer. It's never going to happen. You can't control atoms. It's just too complicated. So this whole progress in quantum is happening really, really quick. So they thought that these ciphers RSA would be deprecated in 2035. Now it's like, 2029. So we don't have 15 years to prepare. And then even when they're here and we replace the ciphers, there's a belief that they could fall in a day. The next cipher change, instead of being 15 years, could be one day. So not only do we have to basically prepare for this better math really quickly, we have to prepare for a world where it could all fall. The next generation could all fall in a minute, a day, an hour, or a week. So we have to kind of move towards this degree of flexibility, or we call crypto agility, where we can swap everything out, in a minute. And that's just hasn't been the case in time immemorial. So it's come this world where, it's coming upon us where you can crack cryptography is coming really quick. And, it seems like most of the movies I watch on Netflix or Apple TV or movies, Mission Impossible, they're all focused on a quantum computer that can crack cryptography. I was watching this new movie called Flight Risk or something last night, 4.5 stars, and they had a quantum computer that could crack encryption. So when it's hit Netflix and hit Apple TV, there's a lot of worry, and rightfully we should be worried, because if you think about it, when I can crack RSA 2048, then theoretically almost all security is gone. It's just gone. Like the planes, it's just gone. So this move now, since NIST's standard board certified that we need to upgrade to this new math, that happened in November. Now there's kind of like a mad rush in terms of how do we do that? How do we take all this old stuff we have and create an infrastructure where we could swap it out in a minute? And so there's definitely, when we started the business, people were like, "You're crazy. Why are you doing that?" And now people are like, "I watch Netflix, or I watch Apple TV about this," and they're like, "We got to get going."
So how likely is it that a person could figure this out and suddenly render our encryption systems broken today?
Well, it's funny. I think there is a kind of belief that some teenager in his basement is going to go, "Oh, why don't I just shift the bits?" And then all of a sudden RSA is gone, and we got a problem.
So with quantum, there's still the physical aspect of all of this. Some kid in his basement is not making their own homegrown quantum machine. It's expensive and complicated. There's also different methodologies. Some are less noisy than others, and they show great potential, but not all quantum computing today is the same.
Microsoft has Majorana, and which is topological, that's less prone to errors. Majorana was a physicist in the 30s, and he hopped on a boat in Rome and never got off the boat in Naples. So we were joking that that's the reincarnation of Bill Gates. That's why I picked it. But yeah, topological qubits are cleaner. There's just variations that have different characteristics. But right now it's kind of a race. It's like two groups digging under a river to meet in the middle. One is working on how many qubits can I create. The other is working on how I can reduce the error rate to get to that magical 4,000 error corrected qubits. And like I said, it's not a day goes by that you don't see an announcement from Google or Microsoft or someone talking about 1,000,000 qubit this or that.
So maybe it was like 2 years ago, I hear these numbers, and then when we get to 100 qubits, everything's over. How close are we to this moment?
Yeah, I don't think it's theoretical. We're not there yet. So to actually answer your first question, how many qubits do you need to crack 2048? You need 2 times the key length. So it's 2048 times 2, 4,100 qubits. A little kind of quantum bit education. When you say a qubit, there's 2 kinds of qubits. It's really important to differentiate which type you're talking about. There's a physical qubit, which is noisy, and then there's a logical qubit. You need 4,100 logical qubits, not physical qubits. So there's a noise ratio. So you might have 1,000,000 qubits that factor down into 4,100 logical qubits. So you need 4,100. Right now, I think the state of the art is, IBM's roadmap is 1,000 logical qubits or 300 logical qubits by year end or something. So we're not there. We're definitely not there. But what's happened in the last year or so is the noise ratio has gone down dramatically, the error correction. So you're starting to see that path to getting to 4,000 qubits, logical qubits, becoming clearer and clearer. Now, with the qubits they have, they can factor prime numbers. They're small prime numbers. So it's not theoretical, like I can use a quantum computer to factor smaller prime numbers, but to get to that magical, 2048 or 4,100 qubits, I'm going to need, those error corrected qubits. But the path is, really moving really quick. And remember, it's just an error correction problem, at the atomic level, which makes it a little harder. But we're just seeing this start. There's executive order came out of the White House a couple weeks ago, and it pulled the date in from like 2035 to 2029, and now you're seeing a almost panic in terms of this is real, and we can't be in a position where we just let all our cybersecurity just disappear. It would be problematic.
All right. Dave's going to have to articulate what is the difference between a physical and what is a logical qubit.
It's physical, but the ratio of physical to logical is collapsing. It used to be 100,000 physical qubits to one. Now it's, in some cases it's a relatively small number. So as they're using AI, they're using other techniques to kind of lower the noise rate. But think about it, if you got to a 1-to-1, that would be really fascinating. It's just, another correlation I like to make is that, right now we process AI linearly with these 64-bit words, right? So if I want to interrogate a neural network, I take 64 bits, put it in a box, put it here, compare it, do all this juxtaposition. If you have a 64 qubit quantum computer, which is that neural net in one instruction, it can be all the data stored in the world in the last year. And I can interrogate it all at once, just in one word, one instruction. So you can imagine the power of just having a 64 qubit, clean qubit in terms of AI or convolutional neural nets. That's the convolutional neural net equivalent in quantum. So.
All right. So Dave mentioned that IBM's shooting for 1,000 logical. There's some talk in the security world, and I'm sure he's heard this as well, where people are breaching systems knowing that today they can't access that data, but they're stockpiling it. And they're waiting for that day when quantum machines are going to be fast enough so that they can suddenly crack all of the encryption. Is that real or is that Hollywood?
Yeah, I was a CIO in my old days in telecom, so I sat on the other side of the table for a long time on how do I keep these assets secure? And there's two interesting stats. First, it said that approximately 25% of the global encrypted data has already been harvested and is sitting in one certain nation state, which we won't talk too much about. The other stat is approximately 25% or only 25% of companies have any idea what cryptography is in their network. They're not actively monitoring it. They don't understand it. It's not inventoried. They don't know where their vulnerabilities are. So in essence, it's the crypto spread in, application libraries and, in key stores. We have customers who have thousands of applications with embedded cryptography and no ability to upgrade them. So one, encrypted data is being siphoned off and moved to foreign places. So when they have enough qubits, they can just crack it. And then two, companies right now, organizations don't have any idea what cryptography is actually being transmitted in their network. Are they on TLS 1.2, 1.3? Are they rotating certificates at a sufficient frequency? What kind of crypto? Is it degraded crypto? Are there key stores that have been compromised? So those two stats are interesting. Being a corporate CIO, I was like, well, we don't even know what we have. And then they're actively siphoning off what we do have that's encrypted. So puts us at a disadvantage in terms of threat. And there's a big argument that, this cryptographic debt we have, or cryptography is embedded in these apps, is like the new malware. right? Because it's all just sitting out there, lurking out there, and we don't even know it. And so, when you do have Q-Day and that it can be cracked, then basically you're going to go after every single one of those apps instantaneously, and that cryptographic debt, which you don't even understand you have, um, it's like a ticking time bomb. It's like a malware time bomb sitting out there.
So Dave mentioned key rotation, which is very important. But is there some depreciated algorithms involved in that as well?
Sure, sure. Um, we've got a transport like TLS, and then we've got the algorithms. Um, and there's algorithmic vulnerabilities. A lot of these applications, when they rolled them out, they embedded the cryptography in them, and it could be outdated, like triple DES or DES, like cryptography that's already been deprecated. There, it's embedded in the program. The company I bought the program doesn't even exist anymore. It's sitting out there, and I don't even know it's deprecated. So they're older forms of cryptography. They're older transports. There's TLS 1.1 and 1.2 who have vulnerabilities. I think they said there was some stat that like 65% of UDP and TCP traffic is unencrypted, like literally just doesn't have any encryption. And so I think we're in a situation where the algorithm could be deprecated. It could be that there's literally no encryption on it. It could be that the key is deprecated. And then, like I said, the worst part is we just don't know in our own internal network.
So when I'm talking to people, some immediately grasp the idea that SSL, that lock that they see on their browser, that's encryption. And it encrypts any transaction that they do while it's there. But there's also the OT ICS community. And I'm interested to hear from Dave what part of the critical infrastructure might be at risk.
Yeah, two really brilliant statements. One, I was talking to the father of SSL a little while back and talking about the mess we're in right now. And the first transaction they had was in one market, the restaurant in San Francisco. And it's because the CEO of Wells Fargo lived upstairs, and one of the guys, his advisor, was the head of online banking at Wells Fargo. And they did the first online transaction at the bar because the CEO lived upstairs. And we were just kind of musing about what a mess it is today. From an OT perspective, so let's think about it this way. Like I have these RTUs in my neighborhood, and they're the devices that control the current flow into your house. And these devices are old. A lot of times they're unencrypted or under encrypted. They're hardware modules. So what you had is what you got. And so if I'm a foreign nation state, and these quantum attacks are going to be foreign nation states attacks, I could literally take over that device and blow up all the devices in your house. So if you look at it from an OT perspective, we're seeing a lot of interest in energy, in everything from oil fields to OT technology and power generation. The OT side of the house is challenged because the crypto is embedded in a device. The devices are almost always old, in many cases completely unencrypted. And then what do I do if I'm a large energy company and I have this enormous investment in OT and tooling? How do I just swap everything out? So we've got some interesting approaches for that. And we're seeing now a realization that if you look at the threat vector, if I'm a foreign nation state and I'm going to attack a country, I'm going to go after their power supply, their water supply, and their food supply first, right? And so all those categories are, heavily reliant on OT, IoT related systems that are generally older. So we can get into a little bit about like how you'd attack this problem if you were, in the water business, or if you were in power generation, or but you can see that the immediate nation state attack vector is power generation and these things.
I think OT devices and the fact that you can't upgrade them immediately pose a problem.
Yeah. So I've spent a lot of time thinking about this problem because it's in my mind a real crux of the problem, right? Like we're working with the government and we're working with DoD and banking and all these things, but On the OT side, I like to think about power generation because I think after 7 days, people start dying, and there's a lot of implications, and a lot of these devices were just not encrypted at all. So fortunately, this transition is about crypto modernization. It's like we've got to look at this problem in a completely different way. This idea of having a cryptography embedded in a device somewhere is just not going to keep up with the changing threat. So if you think about it, we need to create an adaptive infrastructure. How do you do that if you have 30-year-old equipment? Like, how do you create this next generation crypto modernized infrastructure? Fortunately, so let's back up into this crypto modernization. So when I say crypto modernization, it's not just about the new math post-quantum. That's a piece of it, but it's really about putting all the elements of secure communications in place, because the new math is going to fail. The new math will fail. And you better be putting in an end-to-end process that can adapt in real time, that can monitor in real time. What are my changing threats? Has a zero trust framework, has policy enablement so I can control and adapt different layers, has policy adaptation so as these threats change, it's changing in real time. So Lily, how do we get to this thing called secure communications from this place where we're at, where most cyber has been perimeter based, right? I build a wall on something and I just hope they never get over the wall, right? The future, that's not going to work. I'm going to have to actively monitor, understand, and adapt the actual communications that are taking place. So, this idea of being able to orchestrate orchestrated cryptography, or we felt like to think of ourselves as like a SD-WAN for crypto. So a software-defined network, but for cryptography, where you can manage, monitor, adapt, change out in real time and at scale. So let's go back to that RTU in your neighborhood that is a 20-year-old Siemens device or whatever. I'm being extreme. That what you can do, so right now it has embedded crypto or no crypto. What you can do is then, if you're talking to this SD-WAN orchestration capability that can orchestrate the crypto and swap it out, what you can do is put a little wireless device on the actual RTU that has a cryptographic module on it. And so we call ours the next gen cryptographic module. So basically, the 2 points are talking to each other via this module. It brokers all the cryptography, policy, threat intelligence, adaptation, zero trust. So I can basically take a $125 device, wireless device, tap it onto the RTU, and then all of a sudden, that brokers this cryptographic interaction in real time. And then I get the most sophisticated, latest crypto agility, zero trust fabric, policy, all this stuff, crypto agility. So there is we know how to fix this problem. And we're just starting to see a will. This kind of the ability around orchestrated next generation crypto modernization is really becoming a viable approach. And yeah, I'm excited about it. I think we're on that track now where people are like, okay, I need to pay attention to this.
So Dave's solution's interesting. It involves another device that would be mated with the original RTU or whatever to secure it, so that all the encryption goes through that device rather than just the OT device itself.
Yeah, in essence, the device, the RTU, could be, it could be your toaster oven, it doesn't matter. It could be talking unencrypted to this little wireless module on it. And then that module has got the most sophisticated crypto agile key store, quantum key store, the whole deal. It's talking to the orchestrator. So they're talking in the latest math, the latest policy. And all you did was have to buy $100 and something device for the RTU. I'm picking on RTUs, but it can be an oil derrick. It could be, the infinite number of devices that you see out remotely somewhere, so we think it's an elegant way to upgrade OT, IoT, because man, a lot of these IoT devices, you're just cracking into them is not going to be an easy task. You're going to have to have something additive, and you can create just a simple wireless additive module that, like you said, wraps around the pipe. So here's the pipe coming out of the RTU. This just wraps around the edge. You're talking to this thing around the edge. This device still continues talking unencrypted or whatever. It can talk whatever it wants. Doesn't matter. We don't care. And then this cryptographic model just talks in the latest language, post-quantum, or whatever you want it to be.
I'm going to play devil's advocate. And I'm sitting here in Northern California, and I'm thinking, like, we got 750,000 or 1 million people in the city of San Francisco. There's probably more opportunities for RTUs to be in more buildings, et cetera, that aren't occupied. I'm like, if I'm a utility, say PG&E, how am I going to do this? How am I going to upgrade devices that aren't even being used today to comply with NERC or FERC?
It's funny. I did a prezo for the NERC board. I don't know, it was probably 2.5 years ago. And I think to your point, I also used to work for the last CEO of PG&E. Regulated industries move really slowly, right? Like NERC, yeah, so they move really, really slowly. But I think what's happening is you saw Colonial, like everyone's very conservative until there's a material threat. The government has mandated post-quantum in force, mostly for DID and FedCiv. And the actual like NERC, so you see a lot of lethargy, and then you're going to start seeing these threats actually play out in the field, and the government's now come out full force and say, you have to do this. This is a mandate. So if you're in the supply chain for the federal government or FedCiv or whatever, it's now mandated. We could have a long discussion about how quickly PG&E will adopt it. My gut tells me there's all these compliance regimens coming out, like PCI and DORA. They're all mandating crypto agility now. In the financial institutions, they're all basically saying you need a crypto agile network. So now you're starting to see these compliance regimens coming out, and that's what drives behavior. I haven't seen it on the power side, but I mean, we're going to see a real threat play out, and it's going to hit the fan. I think it's going to hit the fan.
This reminds me in 2010 when Obama rolled out smart meters and mandated, more or less mandated, and made incentives for utilities to start adopting it. And the adoption happened fairly quickly. And there was a lot of concern within the security community that, hey, we haven't even vetted these devices and you're installing them in homes everywhere.
So it's funny, I've been in this journey for 4.5 years. You've been talking to Skip forever. And for probably 3.5, probably 3 3/4 of those 4.5 years, people were like, why am I even talking to you? I don't want to waste my time. This is not a thing. It's never going to be a thing. Quantum computers. And then when NIST certified in November, basically saying this is the new math, you need to swap to it, then the standards bodies, these, industry compliance standards started coming out. Use PCI as an example, FIDO, DORA. And so now you're starting this, now your regulated industries, they act because the regulations now say you need to support this. And so crypto agility has been this huge, huge driver towards it. Let me just back into what crypto agility means again. Crypto agility means that now I can swap the cryptography at either point with the press of a button. So if I have 1 million RTUs, I can go, I need them all now to use post-quantum, the next cipher, or a different key length, or a different library, or a different policy, or a different asymmetric cipher like AS to cha-cha. So I think that a lot of this is going to be just driven by compliance, and that compliance is happening now, and that's driving behavior, because we work in banking, and banking was largely we don't care, and then all of a sudden all the regs. I was talking to a big bank, and they said their regulators are in there now saying this is in the front of every conversation in crypto agility from the regulators. Which who would have thought the regulators are talking about post-quantum crypto agility? But so I think that's in power generation. I think it's just driving a lot of behavior towards crypto agility.
So Dave's mentioned this a few times. I want to give him an opportunity to talk about it. Really, it all comes down to math.
The whole area is really fascinating. I said I was a CIO, and then I founded a company that became Oracle's largest cloud partner, and then just wanted to get into something nerdy. I grew up in a very nerdy jet propulsion Caltech family, and mom was a college professor. So although I don't think I ever passed a physics class, I was just super into it. So this whole field of, quantum physics, quantum cybersecurity is just really fascinating. I do want to differentiate I'm talking about post-quantum and crypto agility, that's just better math. It's all software. But there are different categories of quantum communications and security. So there's the better algorithms. That's what we focus on. There's also this thing called QKD, which is quantum key distribution, which is a way for me to use photonic entanglement on fiber, and sometimes like in space down, you can do it over the air, to create a key pair out of photons, which is really pretty cool. So that's really important for like a core network. Like if you're a AT&T and you have terabyte interconnects, it's a great way. There's also this really cool, just from a nerdy perspective, thing called teleportation. And kind of similar to Star Trek, but let me differentiate. So when we're talking about cryptography, we're talking about keys, decoding, encoding. We talk about QKD, we're talking about keys and key pairs. Teleportation is a way for you to transmit data at the atomic level. So it's very secure because I'm transporting it via atoms, photons, regardless. But it's an interesting concept. And the place we understand teleportation from is Star Trek, right? Like, we beam you up and teleport you. And so teleportation is this interesting concept. I want to compare it and contrast it to Star Trek because it's just an interesting comparison. In teleportation, I can take two particles, atomic particles, and I can introduce a third and entangle it. And then the one at the other end becomes the first particle. So that's cool. I can teleport information across the room or across the universe. Really interesting concept, right? Like I can flip a bit across the universe or across the room. Teleportation. Conceptually, I could teleport Robert. I could teleport you conceptually, right? I could say, I'm going to flip those bits in perfect form and recreate every atom in your body across the universe. And unfortunately, it's not moving you from point A to B. It's creating a perfect copy of you from point A to B. So I'd have to kill one of you, or I'm not sure. It's a not as clean a form of as they show you on Star Trek. But eventually communications will be via this form of teleportation, which can transmit almost infinite amounts of data or information instantaneously, perfectly securely. So if you look down the road, way down the road, I don't know that we'll be thinking too much about cryptography or key pairs or key exchanges. We'll just all, data will be teleported. That's way down the road. So that's probably, I think, to have a functional teleportation, it's probably 30 years from now. It's anyone's guess. But so I wanted to kind of differentiate between what we do and kind of crypto modernization to what the future is.
I'd like to thank Dave for coming on the show and talking about how we need to prepare for quantum cryptography, how we need to be crypto agile for the future as we're seeing new algorithms get vetted and then fall by the wayside. This will be a continuing process going forward. The days of keeping AES around for a really long time or DES, those are over. Things are happening rapidly. So being able to swap out your encryption, that's a smart strategy, I think. Hey, if you're enjoying Error Code, tell a friend. I'm sure there are other people out there who like narrative information security podcasts. And I'd really like to hear from you. Go to errorcodepodcast.com to get more details. And tell me what you like, and even what you don't. I've got some great episodes coming up. We'll have more on Volt Typhoon, Salt Typhoon, and hacking utilities supply chains. Subscribe today. I don't want you to miss out.